Thank you very much for coming. It is my pleasure to welcome you all to today's lecture by Dr. Jennifer Wiseman. My name is Nicola, and I represent the VBG, the Christian Student Association at ETH University, and also other faculties, both in Zürich and in other cities around Switzerland. And we're delighted today to welcome Dr. Jennifer Wiseman, and I ask you to join me in wishing her a warm welcome. Okay. Yeah. Now, Dr. Wiseman is an astronomer who's earned her bachelor degrees from the MIT and a Ph.D. at Harvard in astronomy, and she now works as a senior astrophysicist and studies the process of planet and star formation at the Goddard Space and Flight Agency in the US. And she also directs a program on the dialogue of science, ethics, and religion for the American Association for the Advancement of Sciences. So she's a very thin spread, perhaps. And to get to know you a little more, Dr. Wiseman, I have two questions for you that might tell us a little more. Firstly, as an astronomer, perhaps I'm mistaken, but perhaps you must spend a lot of time looking at the sky and looking upwards. And I wonder what keeps you grounded when really all that you have to concern yourself with are the stars and your thoughts are so far from Earth. What keeps your 2 feet planted firmly on Earth?
Deadlines, traffic, paying taxes. No, really, it's a privilege to work in the field of astronomy. So I get to give talks like this and cause us all to kind of look up, because no matter what our daily life is like, it's easy to get focused on the details and the stresses of everyday life. And every once in a while, it's very good to kind of think about the big picture that we're a part of. So.
Certainly, yeah. And then what struck me when I read something about you to prepare for this and all, and your biography is really, to my eyes at least, quite extraordinary. You grew up in the Ozark Mountains in Arkansas, in a rural place as the child of farmers. And it says there that you enjoyed stargazing as a child. And how do you then get from there to being a renowned senior astrophysicist at perhaps the biggest research center for space and the universe in the world, really?
Well, it is an interesting path, but I grew up, as you say, in a rural part of the United States, in the state of Arkansas, which is right in the middle of the country. I grew up on a farm where we raised cattle. I didn't know any scientists, but I loved nature. I loved the natural world. I loved going outside and wandering around in the meadows and the streams and the nearby lakes and rivers. And I love animals, and I love the night sky. We had a dark sky that you could see many stars at night. And so I was very curious about space. I didn't know if I could do something about that, but I had encouraging teachers in my school and other people in my life who encouraged me to go on and try to study science and go on and follow those dreams. Also, about the time I was growing up, these space probes were for the first time sending back pictures from the planets and their moons in our solar system, like the moons of Jupiter and the moons of Saturn. So these were the Voyager space probes you may have heard of. And I was so excited to see these pictures from these exotic worlds. Some of these moons have volcanoes. Some of them are covered with ice. You know, they just seemed like such interesting places. I wanted to go there somehow, either myself or send a probe or be involved in that enterprise. So I think that also inspired me to want to do something related to space exploration. And then also when I was growing up, the first Star Wars movies were coming out. So that got me excited too.
Yeah. Certainly. Well, thank you for your insight. And without further ado, I'll leave the stage to you.
Thank you very much. Yes. Thank you. Thank you very much for the warm welcome. Is the audio okay? It sounds a little bit like it's echoing, but if it sounds okay to you, are you all right? Okay. I'm just hearing everything I say twice, which is really bad. Okay. But I'm delighted to be here with you today. As was mentioned, I have a variety of different kinds of roles. Tonight, I'm here in my personal capacity, just kind of sharing some of my own personal thoughts, not representing any other organization, so that I can kind of get us thinking about some of the meaning of what we're discovering in space. I can share with you some of my thoughts, and you can share with me some of yours. So I have this grandiose title about a university of mystery and awe, dark energy, black holes, galaxies. And one of the astute attendees here realized that your title was originally "and Earth," because he studies Earth and geology. And I changed it to life because that's part of the talk too. But rest assured, we will discuss Earth as well. So I'm very grateful for planet Earth. We'll talk about that. We are seeing such tremendous beauty in the universe with telescopes these days. You know, it's kind of ironic because, I told you that I was inspired by growing up in a rural area where you could see the night sky very clearly and you could see lots of stars. I hope some of you have experienced that, getting away from the city. You have beautiful mountains here, so I hope you've been up and gotten away from city lights and seen the beautiful night sky. But in the last century or two, as we've developed more and more of our urban areas and have more and more city lights and light pollution, fewer people around the globe are ever having this experience of going outside and just looking up and being awe-inspired by the night sky. And that's very sad, I think. Light pollution is basically taking away our view of the universe, and all we should be inspired by that. On the other hand, the irony is that our telescopes are getting better and better. So nearly everyone who has any internet connection can see beautiful images of deep space that we could never see with our own eyes. So this is a kind of interesting combination of good and bad news regarding seeing the night sky and seeing space. This is an example of a beautiful image of the Omega Centauri star cluster, and it, I think, shows off the capabilities of modern telescopes, where by putting telescopes, for example, in space, you can get very clear pictures. You get above the atmosphere around the Earth, and you can get sharp images. The atmosphere of the Earth can blur and even filter out some of the light that's coming through, and so it makes it difficult to get the highest resolution images from space. But if you put telescopes up high on a mountaintop, or even better above the atmosphere entirely, you can see very sharp pictures. So this is an example of a very crowded region of stars. It's a cluster of stars called Omega Centauri. And with the sharp imaging of the space telescope, you can differentiate star from star. If you were trying to look at this cluster from the ground, most telescopes would just show all the light blended together. But here you can see that stars are not all the same. They are different colors. I think of this like a collection of gemstones. It's very beautiful. Now, astronomers look at this with more detail, and they can tell by looking at the color and the chemical composition of the stars using spectroscopy. They can tell the different nature of these stars, the different ages of some of them, the different temperatures of the outer atmosphere create the different colors. If our sun were in this cluster, it would be like one of the small or mid-size yellowish, whitish stars there in between. So there are a whole lot of stars, and if you have the right capability, you can see that they're quite beautiful as well. Here's another region of stars, but these stars have recently formed out of this interstellar gas. in our nearest neighbor, little sister galaxy, the Large Magellanic Cloud. So we've also learned with telescopes that the universe is active. Lots of things are going on. It's not stagnant. We see that stars are continuing to form out of interstellar gas. When you get a little clump of gas in this turbulent material, if you get a clump of gas that's dense enough, that clump will collapse under its own gravitational pull. The hydrogen atoms in the gas, most of the gas is hydrogen, will be compressed by this gravitational pressure. If there's enough pressure, the conditions will be right for a reaction we call fusion. Hydrogen atoms fuse together, forming helium and releasing light. This is basically what a star is doing. A star is a ball of collapsed gas that is compressed enough by gravity that fusion is taking place in the core. The reaction produces heavier elements. Hydrogen produces helium, and it also releases light. And when that light, photons of light, make their way to the surface of the star and escape, we can see the light, and that's basically the birth of a new star. Imagery from space has been inspirational for as long as humans have looked up, and it still is. You can see examples of it all around the world. This is the one of the windows in the United States National Cathedral in Washington, D.C. It's called the Space Window, and all of the stained glass imagery in here is inspired by something about human contact with space and human inspiration from space. We are studying the deep universe and the solar system with different kinds of tools. So telescopes are all needed. They all have different capabilities, different little niches of their own capability, and these work together. So we have telescopes in space. This is the Hubble Space Telescope. It's the most famous space telescope. It's been operating now for 28 years, orbiting planet Earth. Earth is right there, so it's not very high up, but it's above the atmosphere, so that's the key. It can see sharp images because it's above the atmosphere, and it transmits the data back to the ground. There are quite a few other telescopes in space as well. Some have come and gone. We have telescopes on the ground. This is an example. These are the Keck telescopes in Hawaii. They're on top of a dormant volcano in Hawaii, which is on the same island as a volcano that is not dormant right now, but we're hoping the telescopes will be okay. And this is an example of a radio telescope array in South America. This is the ALMA radio telescopes that see wavelengths of light in what we call millimeter and submillimeter wavelengths, and it's very good for seeing into these interstellar gas clouds and dust clouds and giving us lots of information. So these different types of telescopes give us different insight into the universe. Through them, we see different kinds of light. Some of them see visible light, like our eyes can see. Some of them see infrared light or radio wave radiation. Some of them see higher energy light than our eyes can see, ultraviolet light and X-rays, gamma rays. Some of them see small fields of view, so small areas of the sky, but in great detail. Some of them see much wider swaths of the sky, big fields of view, but with less detail. We take all of this type of various information and blend it together to understand now what we're studying in astronomy. I think of it kind of like a symphony orchestra where the conductor will take some information, some input from the violins and some from the trumpets and some from the percussion, some from the flutes, some from the clarinets, which is what I play, and blend that together to get a beautiful piece of music. So the same, I think, is going on in astronomy, using these different kinds of telescopes. No one telescope gives us all the kinds of information that we need. We need the telescopes on the ground and in space and in these different colors of light. I already discussed this space telescope. It's about the size of a of a city bus, and is transmitting information back to the ground as well. Now, we also use the expertise of engineers to a great degree to help design telescopes, especially the ones in space that need gyroscopes and other types of mechanics to help them point and keep stable and give us the information we need. Now, the Hubble Space Telescope has been kept operating well because of a series of visits from astronauts over the years. The astronauts have gone to the telescope in orbit on the space shuttle and have, for several days at a time, done servicing work on the telescope to keep it in good shape. The last time the astronauts did this was in 2009. So this is the cockpit of the space shuttle when they went up and started orbiting the Earth along with the Hubble telescope. There's the Hubble telescope outside the window, you can see there. One astronaut brought with him this telescope. This is a replica of Galileo's telescope, Galileo Galilei. So this telescope was what Galileo used, or something like it, for the first recorded observations of things in space that we know of. And then 400 years later, we have sophisticated telescopes in space. We've had a lot of advances in the technology over the last 4 centuries that have enabled us to build on what Galileo first saw and first described in his notebooks. And I'm very grateful for this use of technology because it's opening our eyes to this magnificent universe that we live in. The astronaut who brought this model up said he was even more impressed with Galileo because he looked through this telescope while he was up in space, and he said that this was actually a terrible telescope and he could hardly see anything at all. So he admired Galileo even more for being able to see something. All right, so what are we learning with our telescopes? Well, I could spend an entire evening on any one of these concepts, that the universe is beautiful, the universe is active, it's enormous, and it's even progressive, and I will talk about this some. All right, so this is a familiar region of the sky. I hope some of you know what this is. Anybody know what this is? Yes? Orion? Yes? See, polite people are waiting to be called on. This is a region of the sky known as Orion. I was recently visiting Australia for the first time in my life, and I was so disoriented because Orion is basically almost upside down there. So it's like, how can this be? But I'm used to looking at it this way in the northern hemisphere, and this is the arrangement of stars here is well known in different cultures. That's seen in different ways, but in many cultures this is seen as a belt and a sword. This is a famous star. In English we call it Rigel, and Betelgeuse up here, the red star. In different cultures and languages they're called different things. I wrote my Ph.D. thesis studying the Orion region because this is what you see in visible and a little bit of infrared light here, but if you look at the same region with radio telescopes, you see something different. You see large dark clouds behind this region where there are new stars still forming. So Orion is very active. In fact, if we zoom in on this little region here, we'll see more detail. This big picture is taken from a telescope on the ground that has a large field of view. We'll look in detail at this region right here and see a small field of view that can be seen with the Hubble Space Telescope. But you realize that this star looks a little bit fuzzy. We call that a nebula. Anything that's kind of fuzzy, we call a nebula in astronomy. So when you look at that little nebulous region, you see this blown up. So this is the Orion Nebula. It is beautiful. It is active. There are new stars that have recently formed. One in particular is very bright, energetic. It's bigger than our sun, and its radiation is hitting the surrounding gas. It's ionizing it. That means it's separating the electrons from the protons. When those atoms recombine, they release colorful light. So we see the beauty in nebulae like this. Astronomers say, oh, this is beautiful, but we also say, oh, this is a sign of recent star formation. Because after a while, the radiation and the winds from young stars will blow away this leftover gas, and there will only be the stars left behind. So the star formation must be rather recent in order to see this kind of ionized gas. More beautiful regions. Everywhere we look, we often see these pillar-like structures in these nebulae. That's because when a massive star forms out of this gas, it will send out radiation and winds that start carving out structures in the gas that's left behind. The denser material remains the longest with the shadowing behind it. So this would mean that some massive stars have formed off to the right-hand side of this image. The winds and radiation are coming back and carving out, blowing away the leftover gas, but the denser clumps can hang on the longest and the protected wakes behind them. So you see often these pillar structures. And in these pillars, you often see lower mass stars still forming. It takes longer for the smaller stars to coalesce and form. So the big ones form fast, start carving out the gas. The smaller mass stars are still forming in the leftover gas. Here's another beautiful pillar of gas, this one in another part of Orion. This image was taken using some infrared capabilities. I kind of wish we could turn down the lights a little bit more. I know that may be difficult for the camera, but okay, yeah, just anything you can do makes, very nice, isn't that nicer? This is the Horsehead Nebula, and in infrared light you can see a lot of this ethereal dust emission in this cloud, and I just think it's quite beautiful. I think it looks more like a dragon than a horse. You can decide what you think it looks like. It's also fun to turn these things in other orientations. There really is no up or down in space, so you can turn this around and it looks totally different. It's helpful to see these things in context. So this is the beautiful cluster of stars I started out with. Yeah, if you can keep the lights down that are on the screen, that would be ideal. I think we're fighting with the videographer who wants light, and I want dark. This is an image to help you see things in context. So this is an image taken with a telescope on the ground that sees a wide field of view. This is looking toward the center of our Milky Way galaxy. So as you look toward the center of our galaxy, there are a lot of stars, a lot of dust and gas. You can see all of that. Some of these objects that look like bright stars, they are actually clusters of stars. And so let's try this zoom on from this image from the ground in this Centauri constellation, and zoom into one of those objects, and then we'll transition over to the Hubble Space Telescope image, which sees more detail. Whoops. You can actually now see that this was a cluster of stars, right? That's the one I've been showing you. This is Omega Centauri. So it helps to see things in context, right? Do you see why we need different kinds of telescopes so we can see? Some people like to do that again. Do you want to do that again? I won't be interrupted by the little message there. All right. I don't like this violent constellation, but all right, there we go. Centaurus. Zooming in, what looked like a bright star is actually a cluster of stars. And then we transition to ever higher resolution, and now we can see the individual stars at the core of that cluster. So context, it's important to see things in context. And when you look at certain things, and this goes for lots of things in our lives, when you look at certain things in a certain way, you may not be seeing all the detail, or you may not be seeing it in its larger context. Old stars are also beautiful and active. So this is a star that is basically running out of that hydrogen fuel. I told you that stars shine because the gas of which they are comprised is going through a reaction called fusion, and most of the gas is hydrogen. But when most of the hydrogen has been converted through fusion into helium in the core of these stars, they start to become unstable. There's less radiation pushing out against the gravity, which is always pulling in. And so then you start fusion of other elements that have been formed in the core there. These processes make the star a bit unstable. Part of that process also causes the expulsion of the outer atmosphere of an old star that's on its way to dying, basically. The star, in this case, is releasing its outer atmosphere in a kind of bipolar fashion because there's probably a disk of dusty material around the star. You can't see the individual star buried in here, but you can see the release of its outer atmosphere. It's a beautiful thing, actually. And some people think that this looks like something. What do you think it looks like? What do you think? An hourglass? That's a good one, yes? There's no right answer, okay. An hourglass. What else? What do you think it looks like? A jellyfish? That's a good one. More? A bow tie, yes. Makes me think of bow tie pasta. Very good. What else? A butterfly. Okay. So there's no correct answer, but it is called the Butterfly Nebula. So, all right. Bigger stars that are much bigger than our sun, when they begin to run out of their inner fuel, they become unstable as well. But the instability is tremendous. It causes a lot of disturbance in that star, and it eventually leads to an explosion. So what you're seeing here are the remnants of a star that has exploded at the end of its life, a massive star. This is the remnant of a supernova. A supernova is that big explosion of a star. The material here is actually material forged in the star and in the explosion. The different colors of this debris from the explosion are being picked up by the filters of the telescope, and it's telling us that the star, through that fusion process, produced not only just hydrogen to helium, but also some heavier elements beyond that, nitrogen, iron, oxygen, silicon. Some of it is produced in the explosion itself. And so the different colors are being picked up by the different filters in the telescope, and the debris is being flung out and made to intersperse or intermix with the interstellar gas that's already there. This particular star exploded about 1,000 years ago, and there were people in China who were watching the sky who saw this. They saw the star brighten up. They made recordings of it. And now we can still see the debris from this exploded star. This is called the Crab Nebula. In fact, we can see debris from other stars that have exploded. Here's another type of image with a different telescope, but you can see this kind of purple material around between the stars. This is debris from another supernova. So this is another supernova remnant. And you can see what it's made of. So remember I said stars are like little factories. They are creating through fusion heavier elements. They start with simple elements like mostly hydrogen. They produce through the fusion process heavier elements, and then they disperse it back into interstellar space. So if you take any region of this debris and look at it more carefully, you can see what the composition is. So this green circle is just around some randomly chosen region of this debris from the supernova, and we're going to look at it with a spectrograph. So spectroscopy allows us to take light, and instead of just making an image, we spread it out like a prism into its constituent colors and wavelengths of light, and that allows us to see what its where the light is coming from, what particular wavelengths of light, and that tells us what the composition is of this material. So when we do that, that material that was circled up here in the supernova remnant is now seen here with in spectroscopy. This is the spectrum of light. The light has been taken and spread out into its constituent colors or wavelengths of light. And you can see the brightness on this axis at each particular color or wavelength of light. You see at most of the wavelengths there's not much brightness at all. But at certain wavelengths, certain colors, you see a lot of brightness. And a spectroscopist knows the patterns. They know the pattern of light that's emitted from different kinds of atoms. So they could recognize, for example, the pattern of oxygen and the pattern of carbon in this spectrum. And that tells us that this swath of gas up here has carbon and oxygen that was produced by the star and is now being dispersed into interstellar space. This is very important. Stars take simple elements and make more complex elements. They then disperse that material back into interstellar space. The next generation of stars that forms out of that gas will have more of this heavier material inside the star. And in fact, some of this material, like silicon and carbon and iron, can actually create solid materials like dusts, these kinds of things, that can be part of the star and also create a kind of disk of material around stars. So these atoms are very important for the formation of planets and for the existence of life. And they're produced, the only way we know they can be produced is within stars. Let's look at some of these regions. So this is back in the core of the Orion Nebula. But if you look carefully, you see some smaller things, not just the big bright stars, but some smaller objects that are blown up here. These are younger, smaller stars that are still trying to form. Remember, it takes longer for smaller stars to form, and it's hard when the massive stars have already formed and are creating a lot of turbulence with their winds and radiation. But here's a couple of smaller stars that are trying to form, finish forming. They're heated up. And you see this dark region around them. These are little disks of material. They can be in different orientations. So this one is face on, and this one is more edge on. They are about the diameter of our solar system. Okay? So these objects were discovered in images from the Hubble Space Telescope and then from other telescopes back in the 1990s. And then ever since then, this realization that stars actually form with dusty disks around them has become a very hot topic in astronomy. The dust here is made of material that must have been produced in previous generations of stars. And of course, we now know that these are planet-forming zones. These are the regions about the diameter of our solar system. And now a lot of astronomers, including many here in Zürich, are studying disks around many young stars in many regions of the galaxy. Often they are studied using different kinds of telescopes like radio or millimeter or submillimeter wavelength observatories, because they can actually see not just the dark silhouette of these disks, but actually see the radiation coming off of them. And in this case, there's a young star in the middle here called HL Tau. And the disk region around it, they can resolve into this whole series of rings. So there's a lot of interest to know if that could indicate planets forming in this disk, because we know in our own solar system that rings around Saturn are the result of orbiting moons. So it may be that rings around forming stars are the result of orbiting planetary bodies that are forming in systems like this. So it's a very hot topic. And in fact, we are finding planets around other stars. This is a very hot topic in astronomy, the study of exoplanets, so planets that have already formed that are orbiting other stars, not our own sun. Our own solar system has its series of planets, but we now know that planets orbit other stars as well. This is profound. We did not know this 3 decades ago, okay? So we didn't know that there were stars, that there were planets orbiting other stars. We thought probably there were. Why would our sun be unique in that respect? But we didn't have the telescopes or the techniques really to find these. When I was in graduate school, we didn't know of any exoplanets for sure until the sort of end of my graduate school years. But now we do, because telescopes like the Kepler Space Telescope have identified many of these planets, also many telescopes on the ground. Some of you in this room are familiar with astronomers even in this country who've been pioneers in finding exoplanets. This is a real system, although it's an artist's conception, because we don't yet have the capability of imaging the planets around other stars with this kind of detail. But the system itself was detected using the Kepler telescope indirectly to find these planets. We are now understanding a lot more about galaxies as well. We understand that galaxies contain hundreds of billions of stars, and that many, perhaps most of these stars have planets. So this is an example of a spiral galaxy. We think galaxies like this have hundreds of billions of stars. There's so many that the starlight kind of blends together in the core. If you look carefully in this beautiful image, you'll see other galaxies here and here and here in the background. You see these beautiful spiral arms. Most of the volume of a galaxy is made up of this a gas and dust, these nebulae that I mentioned earlier. But the mass is largely made up not only of stars, but of something we call dark matter. We don't know what it is, but we see its gravitational effects. Now, we can't get out of our own galaxy to see the detail, but we can look around from the inside to see what we think it looks like. So we think our own Milky Way galaxy looks like this, that it's a spiral galaxy, lots of stars in the center of our galaxy, spiral arms. Our sun would be about here, with our planets like Earth orbiting the sun right about here. But there are probably at least 200, maybe 400 billion stars in our galaxy. And there's strong evidence that the center of our galaxy has a very supermassive, what we call a black hole. Lots of mass from lots of dead stars and other mass compressed into a very small region, creating an extremely intense gravitational field. And so even light could not escape. And you're saying, well, that looks very bright. What am I seeing? Well, this is a lot of starlight around the center of the galaxy. But if you could actually go to the very center, you would not want to do that, because there's something very, very massive and very attractive in that region. We have discovered that the universe is enormous in both space and time. So a single galaxy can contain, as I mentioned, 100 billion stars, maybe 400 billion stars. We don't even know what that number means in our mind. But about a century ago, it was finally determined, after a lot of debate between astronomers, that there are other galaxies besides our own Milky Way, that these little nebulous patches they were seeing in the telescopes were actually other galaxies. Now with our telescopes, we know that there are hundreds of billions of galaxies in our observable universe. One of my favorite images from space telescopes is the ultra-deep field. So this is an image taken by pointing the telescope in a direction of the sky where there are not very many nearby stars. So the telescope could simply receive light for many days without being drowned out by bright starlight from nearby stars. The result is this image. This is the light collected over several days with the telescope. And this is a tiny field of view. This is about the field of view of a drinking straw in the sky. And yet you see thousands of objects in here. These are not stars. These are galaxies. Every one of these little blips of light, the big ones and the small ones, are entire galaxies that can contain billions of stars within. If our Milky Way were in this picture, or if some alien civilization in another galaxy is looking at their deep field and seeing our Milky Way, we would look like one of these spirals here and here. Now, there are a few foreground stars, just a few here and here in the image. Those are in our own galaxy. But everything else here are external galaxies just filling up space. And then you imagine this extrapolated over the entire sky. This is what you would see in any direction, and what we do see in the universe. So the universe is enormous. If you imagine that each one of these little blips of light has hundreds of billions of stars, perhaps, and that most of those stars may have planets, it starts to boggle your mind, right? There's another thing we're learning, though, which is as we start looking at deep fields of galaxies like this, astronomers try very hard to discern the distances of these different galaxies. They are not all at the same distance, right? Some of them are closer to us, and some of them are farther away. And the light has taken longer to get to us from the more distant galaxies. So using challenging but good techniques of determining the distances to these galaxies, we can now imagine what it would be like to travel through these fields of galaxies, just like you were on Star Trek, right? And look at these galaxies that are from farther away in space, meaning you're seeing them as they were farther back in time. It's taken longer for the light to get to us. And you can actually see that these early galaxies from very far back in time look different from the galaxies in our own epoch of time. Could you see the difference in galaxies as we went through? They start to look smaller. They start to look less organized. Here's a different way of seeing this. As our telescopes get better and better and better over time, this is represented going from the top to the bottom here, the cameras and the detectors are getting more sensitive, so they can see fainter and fainter things in space. That translates to being able to see more distant galaxies, because the more distant galaxies are fainter, they're harder to see. That's what these arrows represent. As our telescopes get better with time, we're able to see fainter galaxies, which means we're able to see them at greater distances. Well, greater distances translates into seeing farther back in time, right? Because galaxies at a farther distance from the telescope have taken longer for their light to travel across space to get to us. So we're seeing them as they were when the light began that journey. So the time axis here is on the bottom, going from right to left. This is not a linear scale. We're seeing back almost to the beginning of the universe now with our telescopes, and future telescopes will see even farther. So some of these galaxies you just saw in the ultra-deep field are shining from this epoch of time, which is just a few 100 million years after the beginning of the universe. Nearly all astronomers now agree that our universe, the one we experience, had an energetic beginning about 13.8 billion years ago. There was some kind of burst of energy and inflation at that time, and the universe has been developing ever since. We are now seeing back to within that first 0.8 of the 13.8 billion year history of the universe, right? So we're seeing back to when stars and galaxies just began to form out of gas that had also just formed from the early universe. So we had energy, and then as the universe expanded and cooled, we had atoms, and atoms comprise gas, and once you have gas, you can get the first stars to form, and once you have the first collections of stars and gas, and even what we call dark matter kind of being held together by gravity, we have these proto-galaxies, and we're able to see this. we're able to compare the character of these early galaxies with the character of galaxies that are closer to us in space and time, and with our own Milky Way galaxy, and see if they're any different. And in fact, they are different, all right? When we compare galaxies that are a long way away and far back in time with galaxies closer to us in space and time, we see an interesting progression. So here's that deep field, but pulled out of the field are galaxies now arranged according to their distances. So these galaxies are the most distant. They're shining to us. Their light started its journey billions of years ago. And you can see that these galaxies are small. They're not well formed, and they don't have a beautiful spiral or spherical structure. As you get closer to our epoch of time, you see that galaxies have had time to get bigger. They get bigger by merging with other galaxies. So we now know that merging together is a common part of the history of galaxies. They have time in their rotation and through the tidal and gravitational forces going on to take on bigger structures and shapes, spiral shapes and so forth. Until we get to galaxies closer to us in space and time that are massive, they have a lot of mass. And interestingly, the composition, if you do spectroscopy, if you look at these early galaxies, they're mostly simple elements like hydrogen, helium, and a little bit of other elements as well. But over these billions of years, these massive stars have come and gone, generation after generation after generation. They, through their supernova explosions, have dispersed these heavier elements created in their stars. Subsequent stars have these heavier elements and create even heavier elements. So when you look at galaxies closer to us in space and time that have had billions of years to evolve, these galaxies are enriched. They have the ingredients that we need for planets and dusty disks to form around their stars. Even the elements we need for life, like oxygen and iron and carbon. So we can actually see how the universe has changed over time, seemingly progressing from simplistic material to advanced, enriched material in galaxies that can support planets and even life. So what is this telling us? It's telling us that the universe has developed over time. It's active. It continues to mature and change, if you think that maturing is the process going on to enable planets and life. And over time, this has enabled the production of stars, which have produced heavier elements, and then those heavier elements have enabled the formation of planets around later generations of stars. And that's provided conditions needed for life to thrive on at least one planet. Okay? So we can now see this progressive history of the universe, from simple galaxies to mature galaxies that can harbor planet-bearing stars. And we know that at least one star in our galaxy has at least one planet that has life. We can see this whole progression. It's an incredible unfolding and evolution of the universe. Does that mean that the universe has a purpose? That the universe was always meant to eventually produce and harbor life that can have a conversation like we're having tonight? I have just moved from science to philosophy, all right? I hope you saw the transition, all right? So everything I've said up to now is astrophysics. I hope you're excited by it. It's really fun. We're in a very interesting time. But how do we interpret what we see in terms of its meaning? Does this imply that the universe has a purposeful meaning, that life was always meant to come? That's something that you can't measure with telescopes and microscopes. You can infer it philosophically, but not scientifically. And so you get different opinions about this, even amongst we scientists, all right? So here's an example of the variety of thoughts on this. Steven Weinberg, a very famous physicist, Nobel laureate physicist, said that the more the universe seems comprehensible, the more to him it seems pointless. All right? So is there a purpose? All right? The Templeton Foundation asked a whole collection of thought leaders in different parts of the world this question. So these are scientists and historians and theologians and philosophers. Does the universe have a purpose? And here's a sample of the answers that they got, all right? So all of these people would probably agree with the basic science, the astronomy I've presented, and the biology, the kind of mainstream understanding of biological evolution. And yet when you ask, does this point to a purposeful universe, you get very different responses. Now, each of these answers is also accompanied by a one-page essay, and if you can find this online, it's really quite interesting, because they explain why they've answered the way that they have. And all of these answers are very rich, very interesting to read. I'm just pulling out a few quotes now from some of these respondents here. Well, first of all, you'll see some familiar faces here. So there's some famous physicists in here, like Lawrence Krauss, who says unlikely. Harvard professor Owen Gingrich, he's an astronomy professor at Harvard and also an historian of astronomy. He would say yes. Neil deGrasse Tyson says he's not sure. It depends on what you mean by purpose, and purpose for whom. You know, if it's for the purpose of your gut bacteria, if you ask your gut bacteria, they would say the purpose of the universe is to produce humans so that we can have a nice place to live. So, and then there are some who would say they're not sure. So let's look at a few of these. Professor Atkins, I think he's from Oxford, yes. He said no, and one quote out of his essay said, in the absence of evidence, the only reason to suppose that it does have a purpose is sentimental wishful thinking and sentimental wishful thinking. I've cut that wrong. Which underlies all religion and is an unreliable tool for the discovery of truth of any kind, in his perception. Okay? In other words, this is really not a question we should be asking in the age of science. Professor John Hott from Georgetown University in the U.S., he's from Georgetown or George Washington University. Anyway, he's in Washington, D.C. He says, yes, the fact that we can ask such a question at all, the fact that we're even here, suggests an affirmative answer. The impassioned search for meaning, perhaps our species' most distinctive trait, is not a longing that lifts us out of the universe or that takes place outside of nature. These reflections are part of the universe. He said, we are, after all, as much a part of nature as roaches and rivers. So too is our thirst for meaning. If we accept evolution, as indeed we must, our longing for meaning is nature, in the same sense that birdsong and the howling of wolves are nature. So this question for meaning for him is perfectly natural, and we should assume that that means that there probably is a purpose. Jane Goodall, her opinion is certainly, she said, of course, science typically scoffs at any belief in a God and tells us that we have a God gene and that tendency toward religious belief is simply part of our biological makeup, as inevitable as the universal human smile. Yet even if this were so, we would still have to ask, why? Why should we be programmed to believe in a God? Why are laws of physics designed to make life ever more complex? And where did they come from, the laws of physics? Okay? So you see, different people, all of them brilliant, thoughtful people, can have different reflections on this idea of whether there is a purpose, and whether we see hints of it in our observations of nature. So you might ask, well, how do we think about scientific thought as related to philosophical thought or even theological thought? I like this quote from Sir John Polkinghorne, who is a physicist who became an Anglican priest later in his life and has been writing some very interesting books about the relationship of physics and science and faith and belief. And he said that science and theology are both concerned with the search for truth. In that sense, they have similarities. They believe there's such a thing as truth. He says, in consequence, they complement each other rather than contrast each other. You know, there are many disciplines in our modern society would say that there is no such thing as truth, that everything is kind of relative in context, but there is no such thing as ultimate truth. But the disciplines of science and in some Western theologies both still pertain that there's a right and a wrong answer in their respective spheres of investigation. So he says, of course, the two disciplines focus on different dimensions of truth, but they share a common conviction that there is truth to be sought. I think that's an interesting quote. Let's dig a little bit deeper into this concept of meaning and purpose. And the existence of life. So we now know that there are hundreds of billions of stars in our galaxy. Here's another image from another telescope toward the center of our galaxy with all the gas and dust and lots of stars. And only one of them is our sun. So it would make sense, people have imagined over the ages, that other stars must have planets, not just our sun. But as I mentioned, only recently have we started detecting them. And of course, people have wondered for a long time whether there could be another planet harboring life out there, another Earth. Could there be life? We don't know yet if there's life beyond Earth. But we're excited about the search. And even in our own solar system, we are still finding possibilities of places where we might find life. Recently in the news is a lot about Europa. Europa is a moon of Jupiter. It's an interesting moon. It has an icy crust. This picture of Europa shows cracks in the ice. This picture of Europa was taken by a probe called Galileo some time ago. But recently, telescopes, in particular the Hubble Space Telescope, have seen evidence of water vapor being expelled from between cracks in the ice of Europa. They've been hard to see, and they're episodic, so you can barely see these little whitish plumes here, but these are plumes made of the components of water. They're water vapor plumes. And now going back to the Galileo data, since we've discovered these plumes, scientists have recently announced that when they look back at the Galileo data from the 1990s, they see evidence for disturbed magnetic fields around that region, and also they see that it's warmer there around that region. So there's a lot of evidence that liquid water under the icy crust of Europa is escaping. And of course, we're very interested to know if there could be life in water there, because everywhere there's water, liquid water on planet Earth, there's at least microbial life. So now we would like to know if there could be microbial life in Europa. There's a probe called Clipper that will be sent up there in a few years to actually sample some of this water vapor environment and tell us more. And we're finding potentially habitable planets beyond planet Earth. So that gives us these philosophical questions. How do we, as life on planet Earth, fit into this amazing universe? Are we alone? Are there other life forms? What can science tell us, and what can't it tell us about our place in the universe? The discovery rate of these exoplanets is taking off. So back in the 1980s, the number of these exoplanets that we knew about was 0. And then in the 1990s, the techniques from finding these things, it's difficult to see them, took off until there were starting to be discoveries in different ways over the years. This chart only goes to 2015 because if I go beyond that, the numbers just explode here. But you see the trend, right? So the number of exoplanets being discovered has gotten great. Now, these are not all like Earth by any means, but we were very surprised to actually find that the nearest star to the sun has a planet, all right? So our nearest star system is Alpha Centauri, and it actually has more than one star, and one of these stars is a tiny, tiny dwarf star called Proxima Centauri. So this star is about 4 light years away from us. It would take 4 years for the light to get to us, which is really close in terms of astronomy. And now we know that there's actually a little planet orbiting Proxima Centauri. This is what an artist believes that it might look like if you were on that planet, all right? So lots of imagination. But we now know that planets are common. They're even close. So we're excited to build new telescopes that will be able to tell us even more. It's difficult to take pictures of these planets. Why? Because the star that they're next to is very bright, sometimes 1 billion times brighter than these tiny planets that can get lost in the glare. It is kind of like looking for an insect. We have, I don't know if you have them here. In the U.S., we have an insect called a firefly. They're little insects that emit light. So it's kind of like trying to look for a firefly next to a lighthouse. Very difficult. It gets lost in the glare of the light. There's a firefly. Okay. So we have to use indirect techniques. Astronomers use other ways than just taking pictures to find planets around other stars. The initial way is to see if the star is actually wobbling back and forth, because planets have a mutual gravitational pull on the star. So you may not see the planet, but you can see the star moving back and forth as the planet orbits around. Hundreds of, if not thousands, were discovered this way at first. And then some systems, the planet orbits along our line of sight, so it goes in front of the parent star, and you can actually see the starlight dim just a little bit as the planet orbits in front of it. And of course, imaging the exoplanet, which is difficult, but we're doing that a little bit and building better telescopes. Seeing the star wobble, actually, you recognize that often because as the star moves towards you, its light changes slightly in the received color. It becomes a little bit blue shifted, and as it moves away from you, the light that you receive is a little bit stretched out in wavelength, which means it becomes a little bit red shifted. So if you see this periodic blue shifting and red shifting of the light from the star, you can tell that maybe there's a planet tugging on that star. Here's some astronomers that have used that method to detect many of these exoplanets. All right. And now we know enough, we've discovered enough of these exoplanets in these different ways using space-based telescopes like the Kepler telescope and ground-based telescopes, that we can start doing statistics and find out, what fraction of stars in our galaxy have planets and how many of those are potentially habitable Earth-sized planets. We now know that many, if not most, stars in our galaxy probably have at least one planet. That's amazing, right? We didn't know that before. Some of them are actually potentially habitable. Here's an exciting system discovered in recent years and then are being studied heavily. This is an artist's conception, so we can't see this much detail, and this is not to scale. But these planets are all more or less Earth-sized, orbiting a small star, and several of them are in the right distance from their parent star to potentially be able to have liquid water, so they're not too hot, not too cold. The next step in this whole enterprise is to try to be able to study these exoplanets with better telescopes so we can know more about their atmospheric composition, because they're too far away for us to go to, unfortunately, but we can learn about them from looking at their atmospheres. How would we know if a planet is supporting life? Well, there's a whole new field called astrobiology right now, where we're trying to understand what are the characteristics of life, what kinds of environments could life thrive in, and what would we look for with remote sensing. If we look back at Earth, we would know that there's biological activity on this planet because we would see evidence for oxygen in our atmosphere. Oxygen is being continually replenished by the plant life on this planet and by algae. If we didn't have that, all the oxygen in our atmosphere was very reactive. It would be combining with other elements and we would not see free oxygen. So that's evidence that oxygen is being replenished by photosynthesis. We would look for evidence of liquid water. That doesn't mean that there's life, but it means it might be habitable for life. We would look for other features of the spectrum of light coming from the planet that give evidence of large-scale plant life and other biological activity. We could even see what we call methane coming from biological sources. It turns out that livestock create a lot of methane gas, and so we might find a bovine planet somewhere that's covered with cows. So these are little clues. Of course, you have to rule out that there are other explanations for seeing these things. So this is an enterprise going on right now in astronomy to try to build better telescopes and to try to understand better the conditions needed for life. And of course, we might look at different types of stars, not just sun-like stars, but there are a lot more dwarf stars. We might be interested in finding primitive life because while we're interested in intelligent civilizations, they're probably fewer and farther between if they exist at all, although there is a program called SETI that's actively listening for intentional signals from intelligent civilizations. And most of the planets that we're discovering are really not good candidates for life. They are either too close to their parent star, all the water boils away, they're too far away, they're too cold, they have strange orbits, or they're next to a star that has a lot of violent flares. So we have a lot to learn about whether habitable planets are common or not. And of course, Earth has not always been the same. We might observe an Earth-like planet, but at a different stage of its development. The early Earth, from several billion years ago, had a very different atmosphere than the Earth now. And so we might find different kinds of life at a different stage. Earth had cyanobacteria more than 3 billion years ago. But more advanced life has been much more recent in the history of Earth. And life interacts with the atmosphere of a planet. So we might find a planet at a different stage. This is the history of Earth from 4.5 billion years ago when our planet formed around our sun. And in the early Earth, there was a lot of carbon dioxide in the atmosphere and no oxygen. And over time, these different types of organisms that formed created different conditions in the atmosphere so that now we have a lot of oxygen, a lot less carbon dioxide, and a lot less methane. So you might see another planet at a different stage and still have to recognize whether it's habitable. So this comes us back to the philosophical question, will finding exoplanets and extraterrestrial life affect our view of human significance? And we often get the sense when we look at these images from space that maybe we are just insignificant. Is human life on Earth special, or are we accidental? Are we average? Are we significant? How do you gauge these things? You know, these are some philosophical choices you have to make. What does it mean to be significant? Are you significant if you are rare? Does that make you significant? Or are you significant if you're common? Are you significant if you're central in some way, or if you are unusual? Do you need to be long-lived to be significant? I mean, this is kind of trying to mix philosophy with science, and there's not necessarily a right answer. We all know about the Copernican revolution, where we understood that Earth is not in the center of the solar system, and now we know that the solar system is not in the center of our galaxy, and now we know that our galaxy is not in the center of our universe. There is no center. There may be other universes. There may be a multiverse, and so on and so forth. And yet, ultimately, the Copernican science was found to be compatible with most faiths and cultures. So the question remains, well, if we find life beyond Earth, will that also be something that different cultures and faiths can absorb? There have been some papers recently, in recent years, in the American Journal of Physics and Physics Today, by literary experts cautioning physicists to understand that actually back in Copernican times, in that culture, being removed from the center was not a demotion from significance, it was a promotion, because being in the center was seen as a bad thing. The center of Earth was where hell was, so you didn't want to be in the center. So removing Earth from the center of the solar system was actually not necessarily a demotion. So we have to be careful not to read back into history our philosophy of today. And also interpretations of significance can vary. Rarity doesn't necessarily correlate in an obvious way with significance. The question was asked to different groups as to how they would respond to the detection of extraterrestrial simple life or the non-detection. What if we find out that it's unlikely there's life elsewhere? Are we capable of believing that as well? And of course, we're all curious to know if there could be complex, intelligent life as well. Now, this is not a new question. Greek philosophers were speculating on this a long time ago. Epicurus said there are infinite worlds, both like and unlike this world of ours. We must believe that in all worlds there are living creatures and planets and other things we see in this world. They were using the word world in a little bit different way than we do. What's different is that now we're actually detecting exoplanets. We haven't detected life beyond Earth yet, but we have new data. How are people going to respond if we do find life beyond Earth? Well, a theologian, Ted Peters, asked a lot of different people the question as to whether in their religious faith tradition, if they would face a crisis, if we found intelligent life beyond Earth, would this create a problem? So he asked them, do you agree or disagree? Official confirmation of the discovery of a civilization of intelligent beings living on another planet would so undercut my beliefs that my beliefs would face a crisis. Is that true for you or not true for you? And he asked people who identified as Catholics or Protestants, both the more conservative evangelicals and the more mainline Protestants, Orthodox, Mormons, Jewish respondents, Buddhist respondents, those who said they were not religious. It doesn't look like he asked Muslims, so he didn't ask all religious groups, but a variety. And nearly all of them said they disagreed with this statement, that they felt they could incorporate this discovery of life beyond Earth into their worldview. But what's interesting is he also asked them a second question, which I don't have a chart for. He said, okay, so you think that you can incorporate this in your worldview. What about these other people? Not you, but these people with other beliefs. And nearly all of them said, these other people will have a crisis. Their worldview will fall apart. The religious respondents said that the non-religious people will finally see that there's a great God who has life forms all over the universe. The non-religious respondents said, finally, we'll see that there's intelligent life everywhere and that our foolish traditions of religion and so forth on this planet are pointless because we'll learn from these other intelligent beings. And, everybody seems to think there's going to be a huge change when we find life beyond Earth, but just not to their own beliefs. All right, so something kind of interesting there. What about specifically Christian theology? Would it be able to embrace life on other planets, simple life or intelligent life? Many think so. There's an interesting, intriguing verse in the New Testament that says that Jesus Christ, the righteous one, is the atoning sacrifice for our sins, but not only for ours, but also for the sins of the whole world. And many think that may include life beyond Earth. I didn't realize, but there were actually theologians thinking about this question for many centuries. I don't know why, but they were thinking, there's writings about this for many, many centuries. How do we respond to all of this? All right, human responses to the grandeur and perhaps the bewilderment of the universe can span a huge range, and many of us in this room might have a combination of these responses, right? Some of us feel a sense of wonder, some of us feel a sense of awe, some of us feel a sense of bewilderment. Some people of faith feel a sense of great praise to God. Some feel the opposite, kind of a loss of faith when they see the size of the universe. Some feel a sense of great insignificance. Some feel a sense of gratefulness. Some feel a sense of curiosity to learn more. I hope we all feel a sense of curiosity. Carl Sagan, who is a great astronomer who inspired many of us, he felt philosophically this way. He said, "Who are we? We find that we live on an insignificant planet of a humdrum star, lost in a galaxy, tucked away in some forgotten corner of a universe." All right? So that's that feeling of, gee, now that we know so much about the universe, we must be very insignificant. All right? But that's a philosophical choice. That's not the only response that one can feel. I feel a little more like the writer of Psalm 8, this biblical psalm, where this writer, who was probably a shepherd and had a lot of time to look at the dark night sky, said, "O Lord, our sovereign, how majestic is your name in all the earth. When I look at your heavens, the work of your fingers, the moon and the stars that you've established." First, he had this feeling of insignificance. What are human beings that you're mindful of them, or mortals that you care for them? Who are we? That insignificance. But then he went on and said, "And yet you have made them a little lower than God and crowned them with glory and honor. You've given them dominion over the works of your hands. You've put all things under their feet." Now, he knew that he didn't have dominion over the moon and the stars, and he didn't even know about galaxies. And yet he used that word dominion, and I think the way I interpret this is also the gift of science, the gift of understanding. We may not be able to travel to these other galaxies, but I think it's greatly significant that we're here having this conversation tonight, that we have come forth as fruit of this universe, and that we can actually study the universe. We have the gift of science. We have the capability of understanding to some degree how the universe works, and comprehending it and appreciating it. That, to me, is a great gift of significance. I think I'm going to... I just love this quote. All right, I'll say it anyway. All right. I think this excitement of discovering the possibilities of the fill of the universe is you can see in this quote. Thomas Wright of Durham was contemplating the idea that he had encountered in Milton's Paradise Lost, of this idea that there could be many suns, in other words, many solar systems. And he was thinking about this. And so he was doing a little calculation. Sometimes we scientists will say that we do a back-of-the-envelope calculation. So he was doing this. He says, now admitting the breadth of the Milky Way, he's thinking about it, to be about 9 degrees, and supposing that there's about 1,200 stars in each square degree, and that means there be in that whole area, a little over 3 million stars, and all of these in a very minute portion of the great expanse of heaven. So then you have to extrapolate, and then he goes crazy. Wow! He says, what a vast idea of endless beings must this produce and generate in our minds when we think about this. When we think of these all as flaming suns or progenitors of life, in other words, other solar systems, of a still much greater number of peopled worlds, what less than an infinity can circumscribe them? What less than an eternity can comprehend them? Or what less than omnipotence can produce and support them? And where can our wonders cease? I kind of like this idea, you do a little calculation, a little extrapolation, and then you get very excited. And for me as a Christian, there's an ultimate purpose of all of this beyond just what we can detect with our science instruments. The biblical perspective is that the God behind it all is actually has come to us in the form of Jesus Christ. We call that the incarnation. So here we have God made most manifest to us in the person of Jesus Christ. And it is in this living person that we can actually relate to the author of the universe and actually address the questions that we all have of good and evil, pain and suffering, destiny and hope. The universe is beautiful. Here's another star-forming region out of interstellar gas. The universe inspires us in different ways. I gave a talk like this to a group in Canada. One of the people in the audience was a woman from Iran who is an artist, and she showed me this image she drew that portrayed her view. When she saw images of galaxies, to her it looked like the cosmos dancing. She was inspired by this. So this is her cosmic dance. The universe inspires art, it inspires music, it inspires a great uplifting of our spirits. This is a stained glass window in a church right outside the front door of Johnson Space Center in Texas, where the astronauts went off to the moon and so forth, or the control center is there, I should say. But this church has many stained glass windows with images of space inspired from telescopes. So as we look into the heavens, people can be inspired in different ways. The psalmist, a different psalm in Scripture I like, says, "The heavens declare the glory of God. The skies proclaim the work of his hands. They pour forth speech. Day after day and night after night they reveal knowledge," and yet they're not using words. No sound is heard from them, and yet the voice from the heavens goes into all the earth and to the ends of the world. There's something about looking at the heavens that inspires all of us from all cultures and traditions. And what exactly that is for us to think about. The scientist next to me in Cambridge a year ago in England had this postcard over his desk. He was from Italy, and he said he kept this mural from the mausoleum in Ravenna over his desk. That's his hometown, because the traders coming through Ravenna 1,700 years ago would come into this mausoleum and be inspired to keep God in the center of their lives. Any astronomer and any navigator would know that the circles of stars here represent the apparent motions of stars around the North Star. It's a navigational tool. And yet in this mausoleum, and for the scientist of today in the office next door to me, that was the key to life, is keeping that relationship with the God of the universe in the center of their life. So that's how he was inspired. Any of us, regardless of what your beliefs are, I think can be inspired by the views of the heavens and also the views of the earth. This is a view looking back at the setting of the sun behind planet Earth from the space shuttle, and you see this wispy blue of Earth's atmosphere there as the sunlight comes through it. It's beautiful, but it reminds us that our own planet is fragile. We know there's life on this planet. We don't know if there's life elsewhere yet, but we can certainly all be inspired to be good stewards, good caretakers of the planet that we live on. I can put this up later, but here's some resources if you're interested in how science and faith and philosophy fit together. There's some organizations with great websites that help with this. And I particularly like a couple of these books. The Language of God by Francis Collins, who's actually a geneticist, but he wrote this book about his own journey as a scientist, contemplating the human genome and also his newfound faith as an adult scientist. The Book of the Cosmos is a collection of literature from all kinds of sources, talking about how the universe has been inspiring from throughout history, and I find that a great resource. There's a whole set of organizations here that think about the relationship of science and faith, and I particularly point out Christians in Science here, the American Scientific Affiliation, the Faraday Institute for Science and Religion, the Dialogue on Science, Ethics, and Religion of the American Association for the Advancement of Science. This is a scientific advocacy society. The Dialogue is helping to build better communication between scientists and religious groups. And if you like the pictures, here's where you can see nice pictures. Okay? That's the end of my talk, and I think we have a few minutes for questions, but I want to, on behalf, did someone from the organization want to say anything about this slide, or just leave it up here? Okay. The organization sponsoring this wanted you to know about them and to invite you to something. I didn't know if you wanted to say something about that. Okay, so do we have time for questions?
Just hold up your hand, ask away. We have one here in the third row. Let's start with that one.
Hi, my name is Glenn Behrman. I started out in astronomy. I'm actually an electrical engineer, but I started out in astronomy. And during high school and college, I taught in a planetarium. And for 45 years, I've been telling people, friends with telescopes, stars formed by condensation of gaseous nebula. But if we think about the hard vacuum in outer space, how dense are these gas clouds, and how can mutual gravitation pull this stuff together so that it gets to the density of the inside of a star?
Yeah.
That's part one. And part two is, after I have a supernova and I cook off all my hydrogen and my helium, get into my iron and wherever it's going to go depending on mass, my hydrogen's gone. And then it explodes and I scatter carbon and iron and all this other stuff around. Where's the helium? Where's the hydrogen to form these new protostars, and how does it clump together?
Okay, so these are great questions. The second question, what happens as the stars is really becoming more and more unstable and heading toward this supernova event, is that you actually have different shells within the star that are fusing different elements. So most of the star's life, you've got hydrogen in the core doing that fusion. When you start running low on hydrogen in the core, where the pressure is sufficient to create that fusion, there's not enough hydrogen to create enough radiation pressure to push back, so the star collapses in on itself a little bit more. That creates even higher pressure, which allows the next step of fusion. But on a shell just outside of that, you have the same pressure that allows hydrogen a little bit outside of the core to start to fuse. And this process continues till eventually you get different shells of fusion of the heavier elements fusing in the core, the lighter elements in shells outside of that. So you're never completely out of hydrogen, different kinds of stars. And then most of the material in interstellar space is still hydrogen, so that when the star explodes and enriches that gas, it's still heavily hydrogen gas in which it mixes. And most of the gas, as you say, is very tenuous. It's a very high-quality vacuum, right? So there aren't stars forming in every piece of the galaxy. It's only when you get these denser clouds, again, the material is turbulent, so you're going to get some regions that have a little bit more, some region a little less. Usually that's transient. But if you get a region that has a little bit more density, enough that it actually has significant self-gravity, that the gravitational pull becomes stronger than the turbulence within, then you can get collapse and self-gravitating systems. So you have a few of these. Well, first of all, you have these interstellar molecular clouds, and some of them, it's not really clear whether they are going to be held together for long periods of time or whether they're transient. Magnetic fields play some role in confining or even dispersing some of these things. And then within those clouds, you will get occasionally these eddies that are overdense, and then the gravity will overcome the turbulence. So, but you're absolutely right. The volume, while the volume of these galaxies is filled with gas, that gas is a very low density, a very nice vacuum for the most part. So, good questions. All right.
Maybe upper left first.
Is it possible that there is life that is totally different than the life we know here on Earth? Like maybe life that doesn't need water or oxygen or something like this?
Well, of course. So we have all watched enough science fiction to know that life could be very different. But strangely, in science fiction, they all end up having like eyes, and they speak English, actually. Of course, there could be life that's different from the life on Earth. There are, however, some good reasons to look for life that might have some similarities with life on Earth. First of all, we wouldn't know how to recognize life if it's very different from life on Earth. So we understand, sort of. I mean, we don't really understand life on Earth very well either. It's hard to define it, actually, at this point. But we understand that complex life on Earth does better if it's carbon-based, because carbon is one atom that can form complex molecules that can actually enable complexity. So carbon-based life is a good guess. Everything on Earth that's alive or related to life has some connection to liquid water, which is a wonderful solvent that allows lots of reactions. Water is a good incubator for life as well. Could there be life without liquid water? Well, I need a biologist and a chemist to explain that, because I'm neither of those, but my understanding is that since all life that we know of really requires liquid water to be in the picture somewhere, that's a good place to start, looking for planets that are similar to our experience here, that have liquid water, that have temperatures that allow the existence of liquid water, and that can enable complex carbon-based life to develop. So yes, of course there could be life that we don't recognize, but then we wouldn't recognize it. So that's the problem, yes. Yeah.
Isaac Asimov wrote a book called Life and Energy, which is an essay to look at life from a thermodynamic perspective. And as we're in a philosophical setting, I wanted to ask you what you think about his notion that stars itself could be defined alive, as they have a whole lifetime, they produce excrement, and from that new stars emerge, or maybe in a bigger complexity region, that galaxies evolve over time to be more complex and merge with other galaxies, creating new, and so on.
Yeah, okay. So what does it mean to be alive, right? I mean, this is not a clear concept, and we do use a lot of this kind of life language when we describe stars. We talk about, in my own field of star formation, we talk about stellar nurseries and the birth of stars, and we talk about the lifetime of stars and the death of stars, and what did you say, the excrement of stars? I hadn't heard that one before, but okay. So and yet, stars are not really alive as we traditionally think of life, right? They're balls of gas, So as far as we know, stars don't have feelings. So, and yet, first of all, we don't really understand, especially at the smallest level, what is life on planet Earth. What do you call a living system? It's not completely clear. And then there is an interesting concept, though, that a living creature, such as ourselves, think of your own body, has parts of your body that are not what you would call alive. Your fingernails, are basically dead cells, right? But it's part of your living body. So could you think of the universe as being alive because some components of it actually have life, Is Earth alive because there's life on the planet, and you think of the whole system together, and then kind of step back and look at the whole galaxy? Is life something that exists inside a bigger system, or is the whole system alive because some components of it are alive? Or do you simply determine that life is anything that contains life? So this is kind of philosophical, and I don't have the answer to this, but I do think it's an interesting question. So in some sense, you can say that the universe is alive because we're part of it and we're having this conversation. But on the other hand, it's not exactly traditional life where we think of as life as being biological in nature and reproductive and complex and evolving. So.
Yes, up.
First, thanks for that awesome talk. That's a question I've been wondering for a long time, and I think it has to do with dark matter, which unfortunately you didn't talk about too much in this talk. But why are galaxies flat and not a globe?
Some galaxies are spherical, all right? So let me see if I can... you see, I have different talks, in which case I can show you a lot of great things. But galaxies come in different shapes and sizes, so some of them are these spiral disc-like kind of flattened structures, but even they have a more spherical, what we call a halo, which is a lower density gaseous circumgalactic sphere of stuff. And then there are truly spherical galaxies. It has to do with the history of the galaxy and the interactions the galaxies had with other galaxies. So not all galaxies are flat. They typically take on a flattened disk-like structure because of rotation. There's angular momentum, which tends to create more disk-like geometries of things. You can even see that in our own solar system. Most of the planets are orbiting along the same plane around the sun. I mean, there's some variations to that, but most of the planets are in that same orientation. So most things that have a rotation and are gravitationally bound will take on, at some point, a bit of a more flattened structure. So it has to do with the dynamics over time of these galaxies that can make them flattened.
I'm afraid that's all we have time for. There will be sort of an after thing with apero. Hopefully you can
Actually,
still...
can I add something real quick?
Sure.
I felt kind of bad because I didn't talk as much as I could have about dark matter and dark energy, but let me just say that both of these are very interesting concepts. Dark energy is what we've discovered in recent years that seems, we don't know what dark energy is. That's just a word, a phrase that's been made up to label a mystery, which is that the universe is accelerating in its expansion. We've known for a century that the universe is expanding, the space is stretching, spatial scales are stretching, and that means galaxies are moving along in that space and being pulled apart from each other, basically. But we thought that expansion would be slowing down over time because gravity would be trying to pull all the galaxies back together. And instead, a few years ago, it was detected that the galaxies are actually moving away from each other at a faster and faster rate. The expansion of the universe is accelerating. We don't know what would cause that. So right now, we're just calling it dark energy. Maybe it's some aspect of gravity that's repulsive on large scales. Maybe it's some kind of new physics we don't know about. So that's a very hot topic in astrophysics. What is dark energy? Dark matter is something very different. It's a type of matter, and we can see its effects in many ways. In galaxies, for example, the orbital rates of stars around galaxies is faster than it would be if all the matter were invisible things like stars and planets. In fact, the orbital rates tell you the amount of mass that's interior to the orbits, and it was detected a while back that there must be more mass in these galaxies than we can account for by the visible part. And in fact, we now know that by far most mass in the universe is of this unknown type called dark matter. We see its gravitational effects. We even see it in clusters of galaxies creating distortions in space-time that distort light from the background. So we can map out where the dark matter is, but we don't yet know what it is. So that's something that's a hot topic in physics, is to try to understand. Maybe it's some kind of particle, some subatomic particle that we can perhaps produce in these accelerators on the ground, and that's still a very hot topic as well. So lots of things we still need to understand. So if any of you are looking for a job, we need you in astrophysics. Okay? All right. Thank you. Thank you.
Dr. Wiseman, thank you very much. On behalf of Freiberge and all other organizations.
Thank you very much.
Thank you. Thank you.
Very nice. Very good.
Okay, I'll try to make this short and concise. I must also thank Templeton Foundation, without which none of this would have been possible. They have financed large portions of today's event and have been tremendous in their support. I also thank on behalf of Freiberge the Campus Live and the Dozentenforum who have helped organize today's event. I pray that you don't leave us just yet. We have an apero. If you go up there and then to the left, you can still join us. Hopefully Dr. Wiseman will stick around for a second, and hopefully you can deposit all your urgent questions there. Then you see up here the 3 organizations that have put this thing in place. We also have sometimes weekly meetings in the case of Campus Live and VBG. We would love to have you. We're very open to visitors if you're interested, if you want to ask questions, if you just want to discuss. And then there's also the Dozentenforum for the lecturers and the professors among you. They have a website, which you can see up here. If you're interested, please contact them. They're very open as well. And then this Thursday upcoming, we have 2 different events. Firstly, we have Evensong, which will be sort of a traditional Sunday service held on Thursday evening, along with the theologian faculty from university. There will be communion, music, a sermon, and also an apéro following it. If you have more questions and simply want to discuss a little more, hear a little bit more maybe about faith and other philosophical questions, there is an event in Acri. You will also find a few flyers at the entries, which you can take along with you if you're interested. Please come. We would love to have you as well. The Acri is the Catholic Association of Christians at ETH and university. So if you're more interested in that part of Christianity, that's maybe a good thing as well. Thank you very much for your attention. I know this has been long, and I will not hold you any longer. Thank you.
Thank you.